Okay, that's a little bit of a problem, and I assumed America is the land of equal opportunities accessible to everyone. Guys, is there anything we can do here about it? Okay, better, thanks. Okay, so let's start. Hope it works, yeah. So Shimon was telling you about how he and others are going to build machines that can compute and are immensely complex and learn many things. I'm here to tell you that we already had this amazing machine that can learn and is highly complex, and that's our brain. The only thing is that this complexity of the brain that enables intelligence and high cognitive functions also comes with a great cost and a trade-off. And the trade-off, as you understood from the introduction, is things like post-traumatic stress disorder, anxiety, depression, and many others. And the numbers are big in the US, in Europe, and all around the world. Now, the toll on individuals' life and obviously on society is huge, and what's even more troubling is that it's been on the rise in recent decades and recent years. It's actually a true epidemic. So just as an example, there hasn't been much development in this field, and the main drugs, the main medication that is being used hasn't changed at all in the past 20 to 30 years. It helps some of the people, but not enough. And so it's a major problem yet still. And the point of my talk today is exactly to show you how on one hand we have this amazing learning machine, but on the other hand, exactly because it is so complex and sophisticated, it can result, even with minor misbalances, result in those debilitating conditions. So the brain is a biological machinery. It has a molecular and cellular infrastructure. And if we take as an analog a city, for example, Boston, we can think about roads, cars, buildings, all this infrastructure that make Boston, as well as other cities, a great city. And this I'm going to refer to as hardware in this case, just like a nice computer analogy. But there's one thing that is missing and is highly important for the brain. So if we think about a city, we're still missing an aspect of software as well as in the brain. And that aspect is computing units in the city that can actually communicate through language and make the city alive and vibrant and do the stuff it can do. So in cities, it's actually the people. They are the computing units that communicate, have a language, talk to another. And in the brain, these are nerve cells, neurons that communicate and have a language that talk to. By the way, I asked for a picture of the average Joe. That's what they put here. Not my fault. Completely not my fault. Okay, let's move on. So when we talk about communication between people, I'll use that as an analogy. I think it's a good one. We all know that we can converse, discuss, speak to another person, individual. Two people can do it. It's fun, it's good, we do it all the time. Four people can do it as well simultaneously. We do it in social situations. Maybe kids on Facebook can even go up to 10 or something, I don't know these days. But if we now go to hundreds of people, can we actually communicate simultaneously with hundreds of people? The answer is obviously no, that's impossible. Now, in the brain, the situation is better on one hand, exactly what allows the beautiful machine and intelligence, but also worse when things go bad. So in the brain, we actually have a much larger number of simultaneous units that are communicating and share a language between them, and the number is 10,000. Now just try to imagine for a second This is like all MIT talking simultaneously when everyone hears all other 10,000 people, and every 10,000 people, and whatever one people say, other 10,000 people hear at the same time. And when I say at the same time, I mean sub-second. It's actually at a millisecond resolution. So just imagine it's a crazy thing. Now, on one hand, it's a crazy thing. On the other, this is exactly what allows the simultaneous communication, 10,000 speaking together, what allows what I'm going to call the high dimensionality. Because if we talk about computer science or mathematics, it's actually a high dimensional space of computation, and it's 10,000 dimensions, which is very almost impossible to imagine even. But so this complexity, high dimensionality, I'm going to interchangeably use this terminology, but that is, in our view, the main benefit of the brain, this parallel communication between components that allows it to be so intelligent. Now, what about the number of neurons? That's another thing we need to know about the brain if you want to try and understand that. So here is where the human analogy fails a little bit, and I'll explain why. Because city is no longer a good approximation. If we try and count how many neurons we actually have in this complex brain, well, the numbers range a little bit, but they actually converge to something between 70 to 100 billion neurons in average adult human brain. Now, this number is equivalent to number of people on 10 planets. And I want to make a point here. You can ask me, okay, so why do you insist on this analogy to people? You can think of many other systems that have 100 billion, did I say 100? Yeah, 100 billion components. And for example, in the Milky Way, in our galaxy, there are 100 billion planets. But the point here is exactly the point of communication and language. Just like people can communicate via some language one to the other, so can neurons communicate in the brain one to the other. The only difference, as I emphasized 2 slides ago, is that people can talk to 1, 2, 3, 4, 5 people maybe, and neurons can actually do talk to 10,000 other neurons simultaneously. Okay, so this actual complexity and high dimensionality is, on one hand, what allows our enhanced intelligence, but it also what leads to great vulnerability. And I'll give a very, very, I would say, simple example. So if you think of a group of neurons or a group of people in our analogy, but let's focus on neurons for this. A group of neurons, sorry, that was a mistake. A group of neurons that for some reason got the wrong message via learning, and I'll give some examples soon. It transmits this information and communicates it via the neural language. Again, I'll say more in a few slides, to other parts of the brain, and that spreads almost like a virus, like a disease. Now, because of the high dimensionality and complexity, it's very almost impossible to track and very almost impossible to stop, because there are so many pathways in which it can get to the other region. So the high complexity also leads to high vulnerability, and I'll give a few examples. So we want to focus now into the brain itself and see what we are actually dealing with. I'm going to highlight 2 complementary yet competing systems, which are the focus of my work, and it was very nicely introduced. One of them is the prefrontal cortex, and I'm showing you here only part of the prefrontal cortex. It's actually the cingulate cortex. It's the part that lies right here between the hemispheres. But that's a very interesting part because it underlies learning via rewards and errors. So everything you learn on a daily basis by getting rewards or by getting an error is done with this region. It also underlies attention, decision-making, rule learning, the high cognition functions we're all very proud of and obviously highly evolved in humans and in primates in general. On the other hand, there's the amygdala. That's my favorite part. You should know that every brain scientist has his or her own favorite part, and they would swear on that part, and that's it. So that's my part. The amygdala is responsible for emotional responses, learning, memory, modulation. By the way, it makes my wife always laugh at me because how can my favorite part be related to emotional responses? Whatever. Okay, so, but going back to physiology, and so the amygdala is responsible for the initial, the best way to describe it is that it's the part that is responsible for the initial fight or flight famous response in the face of threat or danger. And now you can start and see, and we've done a lot of work in this, how these two can be complementing in many ways. We need both to have our emotional responses and learn through emotions, but we also need to learn on a daily basis in our ever-changing environment from rewards and errors. And the communication between the two regions is exactly going to be the focus of what we're dealing with. So let's take a simple example. How can normal learning turn into post-trauma or anxiety? And let's say I have a friend, call him Jim. He's somewhere here, and he's, for some reason, few months ago, we had an accident in this very busy road. Some of you might recognize it. It's somewhere around here. And obviously, he's very anxious. On the other hand, I mean, he's right to be anxious, right? If we think about the amygdala and survival, then the accident back then was a good warning sign. He should be careful. Accidents are dangerous for survival. On the other hand, we hope that Jim, since then, went to work again and again every day and crossed the street. And so his prefrontal cortex at this stage should have learned, could have learned that it's okay and to cross the street. So here's exactly what goes in the brain, and that is very similar to what I just described. Once the learning was done a few months ago, the amygdala, every time it faces this road, this heavy traffic road, sends signals all across the brain saying, okay, I recognize this road, it's a dangerous place, behave with an anxious behavior or a traumatic behavior, et cetera, et cetera. Here you see that at the regional level, this is the amygdala, this is the prefrontal cortex, and these are the synapses that go between neurons in the amygdala and the prefrontal cortex. And what's important here is that there's a one-to-one connection, meaning there's one synapse between the amygdala and the prefrontal and vice versa. So they communicate directly. And you can see it in a zoom in and a close-up here. This is an approximation of a neuron. The blue ones are the amygdala ones, the green ones are the prefrontal ones, and they send electrical signals. Neurons communicate by electrical signals, even all across the brain, and they communicate, and in this case, the amygdala says this is a dangerous road, sends too much electrical signals, and Jim appropriately behaves in an actions or a traumatic road. Now, as I said earlier, Jim could or should have learned by now that the street can be crossed relatively in a safe way, and if that was the case, then the prefrontal cortex would have kind of taken command and says to the amygdala, that's okay, you're right, I recognize the road, that you're talking about, but I've already learned via rewards and errors on a daily basis that it is safe enough, and so you can cross the street safely. And this is what we call proper balanced learning. The original learning of the amygdala was a proper one, right? Evolutionary-wise, it was appropriate. Then the prefrontal cortex, more sophisticated learning via rewards and errors, was also proper kind of learning, and the balance between them is exactly what makes normal behavior. We always experience some bad experiences, and then we learn that they are not so terrible just by trial and error, and the balance is usually makes it good learning and proper balanced learning. Now, I want to move on to another example, and that's actually one of my favorites, and that's about generalization, and I'll explain the term in a second in more details. So we have Jim again. This time he's in a completely different neighborhood. He went to visit a friend which lives, choose your preferred quiet suburban neighborhood. He faces again a road. It's a road, right? It has cars, but it's a completely different scenario. It's a much more quiet road. There are almost no cars. There's no real reason for Jim's response to be anxious or traumatic. Yet, okay, I do want to stop and say a few words about generalization here, and that's because I think it highly relates to the two previous talks we heard before, the beautiful talks from Shimon and even from Daniel. So generalization is actually the hallmark of human evolution. If you think about it for a second, it's the essence of learning. It means whatever you learn from few examples, you know when to apply to new situations and when not to apply to new situations, when it's appropriate and when it's inappropriate. Without it, learning would be a simple memory, huge lookup table, which obviously is not very helpful. So generalization is the hallmark of human evolution and primate in general, but human evolution specifically. And maybe the extreme is rule learning, right? We know how to derive rules from scenes and act according to them in other scenarios which are more or less similar to the original scenario. It's also the place, if I may say, and Shimon also hinted to that, where artificial intelligence and machine learning still very poorly, and I say that with emphasis, still poorly fails compared to our brain. We can train machines to do very amazing tasks, but when they have to generalize to new tasks that they haven't seen before, that's where the machines fail completely. And by the way, I think that's part of the answer to the anxiety that was felt here at some point about machines. So generalization is still a major trait of human intelligence, and it is enabled exactly by the complexity and the high dimensionality of the brain network and the fact that so many neurons compute in parallel things. But in this specific case, generalization is actually harms Jim because he overgeneralized. That's the terminology we use. We published a few papers about it. He overgeneralizes from the road, back then the high traffic road, to this other quiet road. Now, what happens in the brain? At the first look, it seems very similar. The amygdala sends, again, signals saying this is a dangerous road, behave in an anxious or traumatic manner, produce anxious like fight or flight responses. In this case, it would be freezing, which is an obvious survival classical response. But the amygdala is actually wrong this time. It's not that it's just saying this is a dangerous space. It's actually misclassifying, miscategorizing, overgeneralizing the previous experience to a new, different experience. Now, you could have expected our sophisticated prefrontal cortex, as I said, that's our most intelligent computational part in the brain, to look at the scenario and say, okay, there are similarities, so I understand your concern. Yours is the amygdala in this case. However, I can also evaluate the statistical properties of this road, the scenario, everything else, and I'm telling you it's safe enough to cross the street in a reasonable way. When this balance doesn't happen as it should, that's where trauma and anxiety can develop. Now, I want to stop here and say something about why do I use these, we can call them mundane examples for things like post-trauma and anxiety. It almost seems like I'm undermining the disorders. And so for post-trauma, I think the explanation is pretty simple. I didn't want to put any shocking pictures here in front of the audience on this stage, but I'm sure you can all imagine what kind of things can lead to real traumatic experiences, and they all rely on the same machinery that I just described, the same computational principles between the amygdala and the prefrontal cortex. So that's PTSD. Now, anxiety is actually a very interesting case because anxiety actually builds, we know now, that anxiety is built on many, many reoccurring, even sometimes minor, they don't have to be minor, I'm just giving an example, but many, many insults, that's the biological terminology, insults to the brain. So it can be just your boss shouted at you at work, your kids have you very nervous for some reason, you have some deadline at work, you underwent a car accident, etc., etc. These are very mundane kind of incidents which should and usually are controlled by proper balance between the amygdala and the cingulate cortex. But in some situations, in some people, these accumulate into and create a misbalance between the amygdala and the prefrontal cortex, resulting in anxiety and in a full-blown disorder that is actually very debilitating disorder. And I'm sure you all know there are several sorts of anxiety disorders. I'm focusing only on one of them here. So there's another interesting aspect to this generalization scheme, and that is that the understanding that it's not enough to understand the balance between the amygdala and the prefrontal cortex and how much this shouts more than this, and that determines the final result. It's actually the understanding that they have to compare and speak the same language so that they know they are talking about the same scenario. And to do that, we need to go a little bit deeper and understand what is the actual code, what is the actual language that I've been saying again and again of neurons in the brain. So what you see here is an example of 5 different neurons, and that's how neurons actually speak one to the other with just like bits in a computer, ones and zeros. And we need to identify the code that underlies one memory. In this case, we're looking after the code that identifies the fear memory in Jim. And we want to differentiate that from codes that are actually symbols, another kind of memory. I'm not sure that the best happy memory you can think of, but each to his own. But my point here is that we want to differentiate between a memory that we do want to take care of and manage in a good way versus memories that we want to keep, because all those memories actually reside in the interaction between the two structures. The only difference is in the code. One of them is by some code, and the other is by another code. And again, this is a highly simplifying figure because I'm showing you here 5 neurons, and actually, if we go back to the beginning of the talk, there are actually 10,000 neurons simultaneously talking, and the code is high-dimensional code and occurs at a millisecond resolution. So that is what we're trying to target these days, and identify the actual codes that differentiate one memory from the other. You can call it the language of memories. Okay, so I'll try to summarize what I told you in a few slides. I'll summarize it in this one slide. And I think we can think of it as few balancing acts that happen in the brain. So we have, on one hand, this amazing complexity of the brain. And I remind you again, we have 70 to 100 billion neurons in the brain. Each neuron communicates to 10,000 other neurons, allowing parallel computing, which allows amazing intelligence and high cognitive function. But sometimes when there's a misbalance in the communication, and in this case, for anxiety and trauma, the balance is between the amygdala and the cingulate of the prefrontal cortex. And so this balance, when it is harmed just by very simple, I would say, bugs in the code, that is actually a good word. There are minor bugs in the code that have an ongoing accumulating influence, and they result in sending the wrong messages from the amygdala to the prefrontal cortex and vice versa. So that's one balance. And the other, I would say, the ultimate goal is to find the actual code of the memories so that we can compare one learning event and memory to another learning event and see how we can differentiate between this event, the over-traumatic or anxious event, and a safety or a happy event. If we can do that, and we have several techniques to target at each of these levels, looking at whole brain in humans with the new 7 Tesla machine that the Israeli family was mentioned yesterday, and looking at the animal models and recording the activity of single neurons and to identify the actual code of the memories, we can then maybe move and target specific memories and restore balance and hence alleviate PTSD, depression, anxiety, so forth. And maybe the final sentence I'll say, and that was said beautifully by Daniel and others, is that in this case, as I think in many other cases, there's a very tight, close relationship between understanding basic science. I started by wanting to understand how the brain works computationally and how our memories and learning represented in the brain, and the path between understanding basic science about the brain and how psychopathologies can occur in such brain is almost, you cannot separate the two. You have to investigate one to understand the other and vice versa. I'll stop here. Thanks a lot. And